Hello. Good afternoon. Hope you've been enjoying the Academy so far. Right. So I was told I was just going to do an AMA, but then I was then told, actually, they don't maybe know very much about Corejam, and the AMA is about Corejam, so maybe you want to tell them about Corejam first. And Corejam is a fairly sophisticated thing. It's actually quite a lot simpler than Polkadot itself, but it's sophisticated in that it's still fairly complicated. So I think it actually makes sense to run through some slides that I made. The slides are a little bit old. Corejam's been evolving over the last few months, so what I'm presenting may not be 100% accurate. I'll try and correct things where I notice the inaccuracies, but you know, in any case, what I present today, even if it's perfectly in line with what there is at the moment, it will almost certainly change before it gets into a state where any of you guys could use it. All right, so you don't need to look too closely to the 2.0 stuff, but Corejam and probably Polkadot 2 in inverted commas, since this hasn't really been decided or anything yet, is likely to include 3 key pieces of technology and probably some other bits that are built on top of it. So the 3 key pieces of technology are Corejam, Safrole, PolkaVM. Safrole is a simplification, is a simplified version of Sassafras, which you may have heard of. It's one of the newer consensus block production part of consensus algorithms. The main advantage with it is that you get a degree of anonymity as a block producer, and you don't have too many forks, like there being a fork in the chain. And so basically 2 blocks being produced at the same point in time is it's almost impossible. I mean, it's not actually really impossible, but it's like basically unless there's a net split, it's not going to happen. Safrole is a reformulation of it that gets rid of a couple of bits that aren't needed. PolkaVM, if you haven't heard of it, you may have heard of it if you've been reading the Polkadot forums, but if not, it's basically a RISC-V based virtual machine. There is an implementation of PolkaVM called PolkaVM, as it happens, which is very efficient, very performant. And it's very handily for you know, blockchains like Polkadot. It does metering dynamically without impacting performance significantly, which is like a big win. So that brings us to Corejam. Corejam is essentially the business logic, the blockchain that Polkadot 2 runs. Now Polkadot, as you've been, maybe you've been learning, I don't know, yeah. I guess you've been learning over the last last week or so. Polkadot is all about providing security to substrate-based chains, parachains. So these chains, they don't get reverted, so they have a good level of security, of finality, but also they can interact with each other, yeah? And the fact that either none of them get reverted or all of them get reverted means that they can very freely interact with each other, much more so than in other interoperability systems, say something like Cosmos, where each chain has its own security and in principle could be reverted, and that would be a big problem for any messages that it's already sent, has already got to another chain that isn't going to be reverted. The same is true for all of the classic bridging systems. So when you see something bridged onto Ethereum, you have exactly the same problem, where the weaker security chain may get reverted, but the higher security chain would not follow that reversion. And so you end up with messages that have arrived, but yet never actually were sent. Big problem. So yeah, Polkadot is basically delivering this service that allows you to build chains. You can send messages between each other without fear that one will be reverted and the other won't. So basically without fear of a lack of consistency coming about. Polkadot, Corejam specifically is a reformulation of a lot of the underlying apparatus that helps us create this system, create Polkadot, But it gets rid of the specific use case of securing blockchains, of securing substrate-based blockchains, of parachains. Rather, this just becomes one of many use cases, there it is, CoreChains, that can be built upon this underlying computation engine, this underlying high security, high resilience computation engine. So let's talk a little bit about what this engine is, right? So we can look upon it as a new interface between quote unquote kernel space, blockchain kernel space, so the trusted stuff, right? And user land, the untrusted stuff. Now at the moment, user land is what a parachain does, and everything else is sort of kernel space. And there's a lot of logic in everything else. Like if you look at it, you look at Polkadot, go to the code base, look at the relay chain on the system chains, you'll see huge amounts of logic. There's the whole of the substrate framework, frame, you've got various palettes, balances and auctions and crowd loans and all the parachain system stuff, and it really is. There's a lot of code in there, a lot of logic in there. If one were try to write something like the yellow paper, a formal specification of this logic, it would probably be sort of years to get it all down. You'd probably never finish because it would probably keep upgrading and changing before you could actually finish the formal spec of the previous version. So Corejam essentially redefines where this boundary is. And what it does is it moves a lot of the stuff that is in kernel space at the moment in Polkadot, and it moves it into user land. And it keeps just the bare minimum in kernel space because we want the bare minimum of trusted code. This is just sensible for various reasons. A big one is, of course, security. You don't want to have to trust that much stuff, right? Yeah, less trust, more truth, right? Is the whole Web3 mantra. So by moving as much as possible to untrusted user land, we're increasing security, and we can improve upgradability. We can make things more general. We can do a lot more stuff on the chain. Another way of looking at this is it presents this permissionless dualism in core on chain. So at the moment, in Polkadot, if you want to upload untrusted code, it goes, you buy a parachain, or you rent out a parachain slot, you lease a parachain slot, you put your code on the parachain and you kind of upload the parachain, plug it in, and it starts going. That's where the untrusted code lives. That's where your code lives, right? You guys as parachain teams. Nothing really happens in terms of permissionless code on the relay chain, on chain in that regard, right? It all happens, from Polkadot's point of view, it's all happening not on chain per se, but kind of, this stuff that's happening in the parachains is getting checked, right? But it's just not getting checked on chain. It's getting checked somewhere else. It's getting checked as like as an extra job for validators to do. And not all of them do it. Some do it, some don't. Yeah? So what we're doing is we're abstracting this idea of the not on-chain stuff that validators do, and we're calling it in core. And the idea is that there are cores, sort of execution cores, a little bit like CPU cores, but consensus within a consensus system, where this computation happens. Yeah? And this is where we get the term in core, as opposed to on-chain. Stuff that's on-chain, all of the validators check everything. In fact, everybody who runs a full node, not just the validators, anyone who keeps the chain in sync does everything that happens on-chain. Yeah? So it's super, super, super redundant. It's also synchronized. Whereas stuff that happens in core, well, there are many cores, therefore it's not really it's not synchronized. Yeah, all of these cores are happening all at the same time. Parachains are being checked all at the same time. I don't know how 50 odd parachains, right? And each of them is executing, being sort of checked, having their execution checked at the same time as all of the others, right? Yeah, it's not happening in sequence. In the same way that when you have a smart contract chain, one contract is executed, and then another contract is executed, and then another, yeah? When it's in core, it's parallelized. And this is where we get scalability. This is where Polkadot scalability comes from. The fact that all of these parachains can all operate, execute, be checked, all in parallel, all at the same time. All right. So, Corejam, where's the name come from? It was originally called something else. It was called something to do with like map reduce. I can't remember exactly what. It's changed to Corejam, and it reflects the four stages that the data goes through. So when you do work within the Corejam model, you first sort of collect some workload to do, like a work package. You then refine it. So you take this big work package and you run it through some logic, and from this big work package, let's say it's 5 megabytes or something, you get some digest, some little bit of data, 4K, say, right? So you're turning like, reducing the amount of data by 1000x. But you're doing a lot of work. This is stuff that happens in core. Then you take all of these bits of work, all of the outputs, these bits, 4, 5K, whatever, and you put them all together. Actually, you switch them all around so that the ones that are actually doing the same kind of work are next to each other. And then you accumulate, which basically means you take a single state, so this is a synchronized element, and you feed them all in and get them to alter that state accordingly. And this is a general model. It's a little bit like map reduce. I mean, it's very much like it in that they're both general models. And it's a little bit like it in that map reduce has this two-stage thing. One of them is parallelizable, and then the reduce stage is obviously synchronized, right? And it's a little bit like that in that the accumulation is a bit like the reduce, right? And the refinement is a bit like the map. The main point of difference is that in map reduce, there is a fixed input. Yeah, so when you push something into map reduce, you're like, well, here's my inputs. It's this, it's A, it's B, it's C, it's D. And they're all going to get mapped to A prime, B prime, C prime, D prime, and then they're going to get reduced with some function where I pass A prime, B prime, and get a result. Yeah? Well, in this case, we don't have A, B, C, and D as our inputs. We don't know what the inputs are. In the same way that on a blockchain, you don't know what the transactions are before the block has actually been created. Yeah? And part of Corejam is collecting the inputs. All right, let's move on. So yeah, Polkadot, we're pretty familiar with this stuff, right? Some of this stuff is relatively new, so we're moving to Agile Core Time, which I believe you've got some idea about already. Yeah? Yeah, grunt. On-demand parachains / instantaneous core time. So this is the idea that you buy your core time just before you need to use it, very similar to smart contract models. Elastic scaling, so you can use more core time as you need it, and your parachain just runs a bit faster for a while. All right. I'm going to talk too much about the rest of it. It's kind of old. So Polkadot 2, moving to Safrole, away from Babe, Agile Core Time, away from this model here. So rather than, at the moment with Agile Core Time, you assign when you buy the core time, you want to use it, you assign it to a para ID, yeah? The parachain that you want to be able to use this core time, right? That's not the case with Corejam. Instead, you assign it to what's called an authorizer hash. I'll talk about this a little bit more in a second. Parachains, well, the whole parachain system actually becomes a bit lower level, and it becomes the Corejam model. The concept of a parachain validation function, this piece of logic that's stored on the relay chain that gets executed off-chain in core, right, to check that a parachain is proceeding correctly. This is now changed, and rather than running the parachain validation function, we actually run the refine function as part of Corejam. It's the RE part of Corejam. And rather than passing what we call a proof of validity block, so a block that includes any of the extra witness data needed for the PVF to check that this parachain progressed correctly. This is now a lower level concept called a work package, just a general piece of work to be done. All right, and what we do is we run the work package through the refine operation to get some intermediate output, this like 4 or 5K of data, that then goes into the accumulation function along with any other stuff that has been, that is useful to be able to put it together with. Right, now, hold on a minute. Just 1 second. This is not formatted correctly. Maybe that is better. Yes. Okay, so there are lots of terms that have become old terms with Corejam and that will be deprecated. Now, before I go and explain all of this, are you at all familiar with any of the old terms? Because if you're not, there's no point even explaining it. Have these come up at all? Yes? All right. Huh? Attestation, okay. Right, well, let's start then. Proof of validity, this is the block that the parachain collators create that basically says, no, it's a valid parachain block, it's correctly transitioned state, and here's the argument why, and bam, it's this 5 or whatever megabyte block, proof of validity block. So this is the untrusted data provided to the relay chain validator group. This now becomes a work package in the Corejam model. Actually, it's not just a work packet. The thing is, because Corejam effectively pulls apart both the underlying mechanism away from the use case, we end up with some of these terms actually having 2 different terms in the Corejam model. We have the sort of higher level term, the more like application oriented term, the term that's specific for parachain stuff. And then we have the lower level term, right? The kind of infrastructural term that isn't specific to the application, that isn't specific to parachains. And so the infrastructural term, the lower level term in this case, would be a work item. Work packages just can have many work items. What this means is that in principle, you can progress many different parachains or do different types of work in the same block, in the same core slice, right? In the same core during the same relay chain block. You can't do that at the moment. At the moment, you can assign it to just one task, one parachain. But in the Corejam model, that's not the case. You can have a work package is what happens on a core during a time slice, during the relay chain block. But a work package can have many work items. Okay. A candidate. When we use it in the term of the consequence of a state transition, the consequence of a parachain, of a proof of validity block happening, or a parachain block, this is now a work output. Because we did the work, we had the work package, we did some work, and we ended up with a work output. This is the thing that's maybe 4 or 5K big, right? And then we also have a work report, which is like a bunch of work outputs. And it's the work report that we attest to its correctness. Yeah? So a work package attestation, or work package, an attestation attests that a particular work package, once executed, results in a particular work report. So the attestation sort of can be applied to both a package and a report, because they come as a pair, right? But an attestation is basically something that our relay chain validator group will sign to sign the work report to say this work report is a valid outcome when you basically run refine on all of the work items from this work package. Yep. And this is what we care about. This is a correctness attestation. This is what it's saying is the stuff that happened in the core at this point in time was correct. Yeah? Whether it's progressing a parachain or doing something else. Now, attestation, when it's used as in the idea of reporting something, I attested, there was an attest. Oh, for fuck's sake. We have power over here. Cheers. Attestation, when it's used like a verb, as in the placement of one of these things, one of these pieces of data, one of these sets of signatures on chain, this is now just called reporting. Because you report it. Now, when you're making an attestation, when you're one of these validators that's making attestation, well, actually we call these guys guarantors, because they're the guys that come along and they say, right, I'm putting some money on the line because I reckon this is correct. Bam. You know, 1,000 dots says this is correct. Yeah. So like when you go in, you're trying to lease your first flat, right? Your first apartment, and the landlord's like, yeah, you know, how do I know you're going to pay your rent? And what they want is, they want someone else, not you, because it's your first time, and you know, who knows, maybe you don't have a job, you know. They want someone who's a bit more established to like guarantee that if you don't pay your rent, they're going to pay it. Same sort of thing, right? It's like the whoever created the work package, maybe they don't have much money on the line, right? So they want a validator who has lots and lots of money on the line to sort of come along and like say, yeah, all right, yeah, it's fine. That's why they're called a guarantor. Now, once it's made its way onto the chain, but before we can do anything about it on the chain, we need to make sure that that should someone protest and say, no, actually this was invalid, we need to make sure that it's available so that all of the other validators, if they need to, can download it and check it. Right? Now the thing that sort of says, I am doing my part, doing my fair share of making sure that this thing is available, for a while at least, is called, well, it used to be called an availability statement. We call it an assurance now, because there's a lot of statements floating around. So just to make it a bit less ambiguous, we say it's an assurance, an availability assurance, as opposed to like a guarantee, right? This is an assurance. Assurance that it's available to be downloaded by any validators and checked. Now, when it's finally been made available and we're ready to like integrate it into the state of the chain, yeah, like when we're ready to basically mark that this parachain, in the parachain use case, this parachain's head data has changed, and it's now this new block. This is called, it used to be called inclusion, which is a mind-numbingly stupid term for what is happening, because it's already been included in the block. It was included a while back. Yeah, it's now been made available, and we're altering the state. It used to be called inclusion. It's now called accumulation, right? Because we're accumulating this state change, yeah, onto the relay chain. Now, we used to say, I mean, we still kind of do, like a collator, the term collator will still be used in the context of parachains. But in the context of Corejam, you know, we're building work packages. We're not collating work packages because there might be no transactions in them. Right? A collator only really makes sense if you're collating transactions, you know, you're bringing together transactions and sort of batching them up into a block. Well, you're not really doing that in general. And so we call them work package builders. Now, after we have accumulated a work report into the state of the relay chain, we also check the work report off chain. And, you know, this happens off chain, but they get checked, and the process of checking them is called auditing. So it's different to guaranteeing. Guaranteeing is getting it onto the chain in the first place. Auditing is once it's on the chain and been made available, is just actually making sure that it's legit, that it's correct. So that's like a kind of secondary checks. I think might be wrong, but I think it's called secondary secondary backers or something in the original, in the legacy. Switch these two. Auditor should go there, secondary should do that. In fact, let me do it now. Auditor goes there, and secondary goes there. Lovely. Okay, good. So, Corejam has a thing called a service. Let me just, there we go. Okay, Corejam has a thing called a service. An example of a service would be the ParaChains or CoreChains service, right? And it's like a kind of use case for doing this in-core, on-chain dualism stuff. It's a bit like a smart contract. You can think of it a bit like a smart contract. There's a few key differences. There's a little bit like a smart contract. So, like a smart contract, you put it on chain, so you upload code to the chain, to the relay chain, right? It's not going to be called the relay chain in the future because it does more stuff than just relaying. And to be honest, even calling it the relay chain for Polkadot 1 was a bit questionable. So it does stuff a little bit like a smart contract. So you can upload code of your service to the chain, and that code is permissionless, and that code can take some input. In this case, a blob, and mutate its state on the basis of that input. Which happens in here. You can store things to the chain, load things from the chain. So far, it kind of feels quite smart contract-y. But there's a difference. In a smart contract environment, you have just sort of one blob of code. Now, it's usually hidden from you. For example, in Ethereum, it's hidden from you. But actually, that one blob of code, although it looks like a smart contract, has many different functions and many different entry points, yeah? Actually, it only has one. It's just that there's a sort of multiplexing system, so it checks to see which one you actually want to call and then dispatches that, right? But in reality, there's just one. So again, that's pretty similar. But there's only one actual thing that gets executed in the smart contract, right? One dispatch agent, one piece of code. It always goes into that one piece of code. Here, there are two. There's refine and there's accumulate. And you can't get to accumulate directly. You have to go through refine. And refine is more or less stateless. What this means is you can't look at your own state. So you can think of refine as a kind of preprocessor, but a very, very high amount, there's a lot of computation that you can do in this preprocessing stage. Indeed, for every core, you can do like 6 seconds or whatever. You could do basically as much computation as you would do in the parachain. And you can do, and in the design that we have at the moment for Corejam, at the moment I think in parachain you can do maybe 2 seconds worth of compute. In the design we have at the moment for Corejam, you can do more like 6 seconds worth of compute. So this is really like, you can do a lot of computation before you get to the point of trying to integrate it or accumulate it into your pre-existing state. Now with this typical, with I think every smart contract platform, these two are combined. You do your compute and integrate it into the state at the same time. So the only function you have is stateful. What we do here is we split them apart so that we have a stateless thing that goes where you can do lots and lots and lots of computation, but it's stateless. And then a stateful thing where you can take the results of that and do more computation a little bit, but it's stateful, so you can read and write from storage, and you can interact with other services. Yeah. So every service has a child tree, or probably it won't be a child tree, it'll probably just be a part of the main tree. And Accumulate has access to that. So again, getting smart contract vibes from this. And if you like a bit of maths, so your posterior state will be the result of accumulating your prior state with the set of the outputs of refine for all the various packages, actually items, work items, sent to your service. So an example of a service is the ParaChains service. And this handles all of the parachains. Yeah? But there may be other services, interesting ones. Now, if all you're going to do is develop parachains, this actually doesn't make any difference. It's like, rather than there being a sort of hardwired parachain service that is Polkadot Relay Chain, there will be a less hardwired parachain service that is the CoreChains service running on a Corejam chain. But it might be that the thing that you're trying to solve is better solved as a Corejam service or something built on another kind of Corejam service than strictly a parachain. All right, so Corejam refinement, stateless, permissionless, and it's variable weight. So this is the thing that takes the work payload and mutates it into a work output, sort of digests it, does some computation on it, and turns it into a work output. This will generally be akin to the stuff that the parachain is doing. It just keeps it chugging along, processing transactions, updating account balances, whatever else that a parachain does. The output is likely to be stuff like, here's my new head, my new chain head. This is my new chain state, and here are messages that I would like to send. Yeah? So interaction points, finality points. This is basically what happens at the moment. It's just not called work output. It's called candidate receipt. Refine has very few, it's almost stateless. I say almost, it's not quite perfectly stateless. It has access to a couple of things. It has access to the state root, or the most recent state root, or the state root at some particular height, perhaps, and it's able to look up a hash. This lookup thing is very important because otherwise parachains, for example, would have no way of, well, no easy way of getting, the parachain service would have no easy way of getting a parachain PVF into the refine function. It actually has, crucially, another function in here, which I don't mention, which is start virtual machine. And it allows, within refine, you to start a new instance of the PolkaVM. And this means that parachains will almost certainly be written, or, be recompiled to target PVM, RISC-V, rather than WebAssembly in the future. It's not a big deal. It's like, just change the target thing in Rust-C. RISC-V, I think, is now a sort of properly supported target. Probably better supported than WASM, actually. I think WASM you still need nightly. What else does this mean for parachains? So there's one other very useful thing. Because PolkaVM is metered, it means that you can, in most instances, get away without doing benchmarking. You don't kind of need weights so much. Say so much. There are instances where, yeah, you might want to introduce them. these are basically either when it's when you want to optimize it heavily, or when you've got something that might take a really long time, depending on untrusted inputs. And you want to check that it's not going to take like really, really long, more than the block might take, before you start executing it. But if your operations are basically bounded, and you know they're bounded, and you know they're not going to take very long to execute, then it basically frees you from having to do benchmarking, which is a pretty big win. All right, so then you've got accumulate, and accumulate is the bit that actually brings all of the refined results together. Now, in the context of parachains, what it does is basically does all the message passing, right? It manages the underlying XCMP magic. That means that parachains know what messages are coming to them, and they're able to send messages out. Stateful, there's lots and lots of things that you can call, and it's still permissionless, but there is a sort of preset weight, like you get told how much gas actually, not weight really, you're allowed to use. I use gas for when things are metered, weight for when things are benchmarked. So yeah, there's a few calls here. Interesting one is checkpoint. Checkpoint basically says all of the state changes I've made so far, regardless of what happens, even if I run out of gas, they should go in. Now, smart contract platforms like EVM-based platforms don't have this, right? In these platforms, if they run out of gas or panic, whatever, everything gets reverted as though it had never been called in the first place. So we put this in so basically you can do optimistic processing, right? You can process some stuff and say, well, I don't know how much more gas I'm going to need to process the next load of stuff, so I'm going to checkpoint my work here and then just try, and if I run out of gas, well, never mind, I just get reset back to my checkpoint. But if I don't, at least I've managed to process some more stuff, and I don't need to know how much gas it might take beforehand. You got some storage and stuff. To be honest, I won't look too closely at these. They've changed a lot, and I didn't have time to date them. Right, so, all very well so far. Services, very good. Assign things to a service, very good. I'm a parachain on the parachain service. Suppose I want to buy myself some core time, then what do I do? Well, it's a bit tricky because there isn't an identifier like a para ID in the Corejam model, right? Because a parachain is an abstract entity inside of a service on Corejam. Corejam is a second-class citizen now. Corejam has no idea what a parachain is. It just knows about services. Instead of having para IDs, or as they were called, task IDs in an earlier iteration, we have, this is actually wrong, we don't have an auth ID, we have an auth hash. So it's a 32-byte hash, right? And it's a hash of something that describes some work that can be done. It looks a bit like this. So there's your auth hash. That's just a hash of this structure. The structure has two things in. It's got code hash, which is a piece of code. Runs in the PolkaVM, and it basically just returns. It's got a single entry point. It just returns true or false, and it accepts a work package. Basically, there's a few extra bits in there, but it basically says it's a function that answers the question, here's a work package, is it allowed to be executed or not? And then there's a param as well, so this gets passed in with a function. This might be something a bit like a para ID or something, so that you can easily parameterize the function without having to just upload lots and lots of different versions of the same function, but with one different thing changed. And this, you hash it together, and this becomes the auth hash. And this gets stored on chain, and it gets stored alongside, in a sort of queuing mechanism, each core. So each core has basically a queue of these things, these auth hashes. Yeah? And If you just want to take a core and just always use it for a particular parachain, which is what happens at the moment, then it's just going to be the same hash. It'll just be a hash that basically looks in the work package, make sure there's a single work item, make sure it's a work item that progresses this parachain, yeah, and then returns true if all that's true, and false if it's not. Very simple authorizer. But we can imagine very complex authorizers, or more complex authorizers, things that, for example, look for the right signature set, or look for a proof that it's the right, that the collator was correct. Or look for proof that a particular amount of gas was used, or a particular job was done, or that maybe instead of just there being one parachain, maybe there were 2 parachains being progressed in the package. All sorts of much more complex potential work descriptions could be made using this system than what's possible at the moment with just a straight para ID. So yeah, this is what the is authorized looks like. So it basically says, hey, I'm on core whatever. Here's a package. Here's the param. Is it true or false, right? And this happens in core. Doesn't happen on chain. On chain, all we care about is the hash, because if ever a guarantor does work for which they were not authorized and presents it as being authorized work, it can be disputed later in the same way that if they do the work incorrectly, it can be disputed later. So we don't care about putting all of this stuff on chain. All we care about on chain is just remembering what the hash is. Yep. Good. All right. Oh yeah, I'm not going to talk, we got rid of some of this, so that's not so important. That's what a work package looks like, more or less. Got some authorization information. This is the thing that gets hashed, that hashes to that auth hash thing. Some context about what's going on the relay chain around the time that the work package was being made, and then the work items, which are basically just bits of data with a service identifier. Yeah, and we can make sure that there is another work package that has already been processed by the time our work package hits the chain. Yeah, as I say, a work item, very simple thing. It's got like, this should be service ID, and then a payload, right, which is just a blob, just a bunch of data. It doesn't care. It's like a PVF or whatever, but it doesn't care. Sorry, not a PVF, a POV. Blah, blah, blah. So yeah, this is like the information concerning a package. Again, not much to see there. Work result. So, you know, service identifier, the hash of the bit of the blob of work that was done, the result, which is basically another blob or an error, the gas that was used, and then the error can be 2 things. It could time out, which basically means out of gas, but this was before we had PolkaVM, so and then otherwise panic. Cool. I think the rest of it is probably not that much point talking too much about it, because a lot of it has changed. So authorize in core, refine is in core. So in terms of a work package working its way through Corejam, first it gets authorized. You check to see if it's allowed to happen on this core. Then you actually refine it into some blob, some work output, or set of work. It's actually a work result. Then it goes on chain. It gets reported on chain. And then off chain, availability happens, and all of the validators distribute the pieces of the work package so that it can be reconstructed if needed later on. Then off-chain, there's some like cunning work package sort of sorting it out and building and checking which ones need to be executed. And then basically on-chain, thing happens and it gets accumulated, right? You can ignore 5 really, that's not so important. So authorize, refine, you get the work output, the work result, gets reported onto the chain, made available, and then once it's available, it gets accumulated into the service's state. And of course, part of this can involve sending messages to other services, so the services can interact in this way. Not going to bother talking about initial validation. I don't care about ordering so much. I think that's it. Yeah, cool. So what's the use cases? Well, CoreChains is the obvious one, right? Parachains on Corejam, doing what Polkadot does at the moment. We can imagine a service, CorePlay, like an actor-based environment on Corejam. What's the advantage of doing it on Corejam? Well, the main thing, as opposed to a chain, the main thing is we can make it asynchronous. When stuff's on a chain, it's synchronous, right? Chains are fundamentally linear devices. Yeah, they're single-threaded. Yeah, they're synchronous. Corejam is fundamentally async, parallelized. Yeah, it's got however many cores, all executing at the same time, and then eventually accumulating the outputs of these cores into the state on chain. What it means is that we can do things like split actors onto different cores at any given time point, and then reconfigure them at the next time point. Yeah, so it might be that we have actor A using one core, and actors B, C, and D sharing a second core at time point 1. At the next block, it could be actors A and B sharing one core, and actors C and D sharing one core. Yeah, and then the next block, it could be actors A, B, and C sharing one core, and D is actually just sharing one core. Yeah, we can move them around very, very simply because we're not tying the idea of the state, blob of state, onto a core. Yeah, and this is a very interesting proposition, I would say, in this world of blockchains, because we're finally freeing ourselves from the idea of a synchronous computation device, without going to the sort of extremes of the Polkadot did, where it's like, well, you've got many different chains and they're all running in parallel, but it's kind of a pain to make them talk to each other. We're going to talk about that tomorrow. Good. Okay, I think I'm done presenting, but I'm happy to switch to AMA format, and we can, if you've understood any of it, you can start asking me about the bits that you didn't understand. Yes. Go on then, Phil.
Yeah. Hey.
Hey.
So because you can now do more synchronous stuff with this than we could before, does this reduce or even eliminate the need for accords or spree? Because now you can get like different chains doing things together. Like I could do a flash loan on one chain and act on another chain all synchronously. So do we need accords in the future at all?
I think so. The idea of accords is just the idea of rules across asynchronous state transition systems. So chains, different chains having rules that they all adhere to, permissionlessly, trustlessly. And I think that broad idea hasn't changed. Right? In my mind, there is still very much accords are still useful, but what's changed is how we get there. I don't think we need spree to get there. I think Corejam basically replaces the need for spree. Why? Well, because in the work package that executes your parachain, you can include another work item, which is a spree module or an actor, right? And then these two can then synchronously interact, and then in a later block, that actor can synchronously interact maybe with another actor of its kind that was synchronously interacting with another parachain at the time, or it can just enforce the same kind of rules as spree, and then maybe, I don't know, there's only one of them, and they move between like a kind of, what do they call it, token ring network, one of these old networks in the 70s where it's like there was a sort of speaking shell, and you had to hold the speaking shell to speak on the network. Well, it could be something similar where there's like a sort of spree shell, and you have to hold the shell to interact with the spree module. So there's a few different ways of doing it, but the nice thing is that Corejam enables all of these ways, and you can experiment, find whichever one suits a particular use case the best.
Cool. And I have one more unrelated. So like we're coming from this mindset of, the relay chain being, super light over time and reducing its functionality and being as meta protocol-ish as possible, with like a lot of the execution and storage being done on the parachain level. That's where we're coming from. And if we're now able to do different like work items and work packages that aren't just, it could be like smart contracts and other type bits of code directly on the relay chain, or on cores on relay chain, where exactly, since they're not like parachains, where like are there PolkaVM nodes? Like, is it that much different than before, where you have parachains that store the data and make it available? Now that we don't have necessarily chains doing that anymore, what does this look like?
So there's a few models that I can imagine, but you're right that the state of this machine, if it doesn't live on the relay chain, and it probably doesn't because the relay chain is busy with its own state, must live somewhere. And if it's not in the group of validators, group of collators that are keeping the parachain going, in the parachain's case, where does it live? And the thing is, what we can imagine is, for something like CorePlay, I see two possibilities. One of them is that the state, it could just be that we ping the actor every 24 hours, right? So you've got 24 hours of distributed availability that Polkadot provides you. So the work package is, I don't know, 5 megs or whatever. And you just say, right, well, 2.5 megabytes of this will be used for prior state, 2.5 for posterior state, and because normally we'd use all of it for prior state, but we can't do that if we want to use it for basically holding the posterior state so that anyone can come along and nudge it along further. And then, yeah, you just go to the distributed availability system if you can't get it any other way, and pick up the 2.5 megs posterior state. That's your state that's the state of the contract now, and you do whatever you want to do on it in CorePlay. And so you don't actually need nodes because you've got the value sort of kind of abusing the validator, this DA service. That's probably fine, but it does limit you to 2.5 megabytes of state, which is kind of pretty limiting. It might be fine if you're going to use lots and lots of actors. Like, I don't know how many, there's probably plenty of smart contracts or smart contract-like things that you might want to write that would fit into, whose state would fit into 2.5 megabytes. Think time locks and multi-sigs and all this sort of stuff. These are easily fit into 2.5 megabytes. But for smart contracts that are much bigger and maybe don't fit into that space, then you'd want some other sort of decentralized data provisioning service, like data serving service, that lasts maybe longer than 24 hours. Now for this, probably, I've got a few ideas, but probably the most obvious one is the bulletin chain, which is itself a chain-based service that stores data for about a week. And then you basically have an unlimited amount of data, so your contracts can now, not contracts, I shouldn't really say that, actor can fetch whatever it wants. It only has to be pinged every 7 days, and maybe it sets up a sort of service, so it just stores the data indefinitely. Just keeps re-entering it every 7 days without the actor being pinged. And the nice thing is that using the PolkaVM, we have page tables and all of this nice stuff, which means that the actor can have paged memory, fetching from this DA, this sort of extended DA service as needed, fetching its state as needed. And of course, this would be done in the work package builder stage. So the work package builder would be running the CorePlay actor, working out which pages it needs, putting those into the work package with a proof that this is indeed correct, pulling it from the XDA service. But from the point of view of the actor, it's totally opaque, right? It's like all they think is that they've got lots of memory. And it's just a regular code, like function main, they just run through it, they can allocate whatever it just works. And this is kind of nice. We sort of break away from most, if the vast majority of the on-chain limitations and idioms and all of these like gotchas and foot guns that you know that make it a bit taxing and difficult. All right. Yep.
All right. So, Dr. Wood, could you share your thoughts on the feasibility and potential benefits of using something like ARM64 for compiling core time compared to RISC V, more or less?
I'm not an expert on RISC ISAs, so I can't really give much of an answer, I'm afraid. The main reason, as far as I know, that RISC-V was selected was because it has a variant where you get 15 usable registers if you don't need an operating system only. And this means that it's you can make a one-to-one register mapping with the x64 machine architecture.
Gotcha. Sorry, I thought, but I was going to say, I only bring up the fact that the potential for ARM64 due to the fact that Apple's new M-series processors are on the ARM64 architecture. And I've heard nothing but good things about the performance boost of the M-series processors for something like a Polkadot runtime. So.
I mean, you know, the ISA is really different to a CPU's specific implementation of it, right? The ISA is just an interface. Right. And so the fact that Apple have made a really impressive implementation of an interface has, I mean, you know, obviously it can't be a terrible interface, but it doesn't have so much to do with the interface itself. I'm sure if you found those very same engineers and you got them to use the same tricks under a RISC-V interface, then it probably also makes something pretty special.
Thank you very much.
Hey, in terms of existing parachains, what will they need to do in terms of to adopt new paradigm?
Not much. Recompile for RISC-V is the obvious one. There will probably be a significant frame upgrade coming towards the end of the year, probably early next year, that will allow for basically benchmarkless dispatchable functions. So a way of sort of marking the weight of a function as like just meter it instead. Now the way that the way that this would work is that you actually still need to give it a maximum, but you can set your maximum to like 1/10 of the block weight or something if you're certain. As long as you're certain that a single dispatch isn't going to use more than like 1/10 of the block weight, then you're fine. Other than this, it should be pretty straightforward. There are one or two actually. Yeah, I forget. There are one or two other things. So the way that XCMP is currently implemented, internally known as HRMP, essentially passing datagrams between parachains via the relay chain. This doesn't work under, or it doesn't work very well under Corejam, because the work output is a fixed size. Like it must be no greater than whatever 4 or 5K. Which means if you want to send a message that's more than, I don't know, 2 or 3K to another parachain, can't really do it using Corejam. Now, you shouldn't really be able to do it using Polkadot 1 either, but we've sort of fudged it so that as long as there aren't too many parachains doing it all at the same time, it kind of works. Now this is a fudge, and the idea is that we implement proper XCMP whereby the data itself doesn't go via the relay chain, it uses an off-chain channel between the parachains. But this isn't implemented yet. So this is something that will need to be implemented for Corejam, and it's can be expected to be happening in the background as Corejam and CoreChains gets developed. But from the point of view of parachains, realistically, it's more of, make sure you upgrade to the latest substrate rather than anything else. There won't be that many alterations in terms of APIs. The main one will just be, the main sort of thing will be update to substrate, recompile to RISC-V, maybe run a script, and then it should be it. It'll be a big deal, but it won't be a lot of coding.
Okay, makes sense. Thank you.
Thank you. So I know there's kind of like some reluctance with the term Polkadot 2.0, but at Decoded, when you shared your vision for Polkadot in the future, one of the things that you had mentioned, which I didn't see here, was accords. And so I was just wondering if accords are still a part of the current vision for the next iteration, and if so, how would you see them like in the timeline playing in, and if not, when would you see or hope to see them come into the picture?
Yeah. So accords themselves as a high level concept, I think, are still very relevant. But rather than being implemented through Spree, which is very particular kind of thing designed specifically for parachains, then they'll likely be implemented essentially via a different type of service. A sort of an upgrade to the parachain service or an alternate service that allows for, that basically implements Spree, but does so using this new abstraction framework that we have. So it's, in my mind, this has to be done. Corejam is sort of something that once implemented and moved over to CoreChains, basically makes Spree 10 times easier to actually do.
Thank you.
Can I go? I have a question. What's your secret sauce to creating and, more importantly, shipping systems that don't care? What's a good template that all of us can use?
So this is a hard one because it's, you're designing systems of rules and you're looking for the emergent effect when humans interact with these rules. And designing rules to give an emergent effect is like super difficult, weird reverse engineering of human behavior. But there are some, I think, to a large extent, you need, imagination, you need some experience. But I think one of the ways that you just got to constantly be thinking is how, if this were a game and I were trying to play this game to win, how would I win? What strategy would I use? And as long as the strategy that you used in order to win, if you're being as ruthless as you could possibly be, results in the emergent effect that you're after, then you're good to go. Now, if you end up with trusted elements in the system, and quote unquote ruthless behavior includes various attacks that would allow you to take over private keys, then you've got a problem. This is why, or even if as a malicious actor you don't take over the private keys, but maybe just the environment dictates that the person with the private keys either goes offline or goes mad, or is compromised in some other way. Again, your system is broken. So it's always about trying to imagine worst case. Yeah, whether it's the most ruthless attack that you can think of as you sort of playing devil's advocate and being an actor, or if it's just environmental factors. It's always about understanding, like, and imagining what the worst case is and playing it through. So I don't know if we've done it this time, but one of my original ideas for the PBA economics and game theory section was to have everyone play some like basic strategy board games and like try to start understanding what emergent effects come about because of certain relatively simple rule sets, because that's really what it's about. Did you play any strategy board games? No? Okay. But you played some games, right? Play some little games. Yeah, but I can't really give a much. There is no magic source. It's really a case of imagination and knowing your tricks, knowing your cryptography, your cryptographic tools, knowing your game theoretic tools, and sort of putting the pieces together, and then working it through in your head, and then obviously for things that really matter, doing stuff crazy, bigger scale experiments like Osama, where you're actually trying to, putting value behind testing frameworks, testing networks, and just trying to see what breaks as people use it. But it's difficult. It's hard.
Hi, Owen.
Yeah.
You mentioned that parachains, which would be CoreChains, will have like instead of approximately 2 seconds to do the logic, 6. Are you expecting like a 3x improvement in block space, or?
Yeah, pretty much.
Yeah.
Yeah. I mean, of course, this is for parachains. A parachains block is not going to take 6 seconds of computation. Like, parachains will have to be parachains will have to be collated on faster machines than what the PolkaVM machine is, so that it only takes whatever 3 or 4 seconds to actually execute. Otherwise, they would never be able to make a full sync because they would always be running behind. Like you'd never be able to, you might warp sync to like close to the head, but then as you execute one block that takes 6 seconds, a new 6-second block has been added to the head, so you'd never actually synchronize. So you have to like have some divergence, the actual execution time of a block needs to be lower than the work done in the block. Yeah, than the work notionally done in the block, or than the block period. But realistically, the PolkaVM is not going to run at native speeds. Probably it's going to be around 45–50% of native. So as long as you have a pretty decent processor, pretty beefy processor, then you'll be able to synchronize faster and produce blocks faster than the relay chain, or whatever the new name for the relay chain is, can check and finalize them. But yeah, I would expect a substantial increase in block space from what we have now.
Thank you.
Thank you. Hi.
Hey.
My first question, I have two, is regarding the use case. So Corejam, and the whole idea is to make Polkadot more efficient. So communication is faster and async, and basically making the system better, right? I think that's a clear message, but what about the other use cases? So when someone comes to me saying, hey, Six, tell me about this new feature of Polkadot, I heard it's really great. Is it the only use case we shall communicate, or there are other use cases like the execution? And if it's execution, for example, how does it relate to the system chains? Because my understanding was that system chains were created because we wanted to move execution out of Polkadot itself and kind of make them exogenous, so there is more or less execution in Polkadot itself. And now I see that there is a VM and there is more execution actually potentially coming to the relay chain. So could you please clarify how does that part work?
Sure. Okay. Firstly, it's not about efficiency. It's about generalization. Now, there are efficiency gains, but they're secondary. You can't implement CorePlay on Polkadot as it stands. Just can't do it. With the under the Corejam framework and the Corejam execution model, you can do it. It's strictly more general. Yes, there is a VM now on quote-unquote the relay chain. However, the VM is pretty simple. I think it's around 23 instructions in the RISC-V 32EMC or whatever instruction set. And those instructions are things like add, sub, shift left. You know, it's like, it's very, very minimal VISA. There is a lot less logic and a lot less opinionation than what there is on the relay chain at present. That's ignoring the system chains, which have taken some of the stuff off the relay chain already. But if we even just look at the parachains specific logic, we ignore staking, we ignore crowd loans, right? It's still a huge amount of logic. Replacing that with a VM actually reduces the amount of complexity. And I say this as someone who's writing a spec on the relay chain, on this main chain. And the nice thing is that the one thing that is a little bit troublesome, maybe not. Okay, so in the past there was the idea of like, right, Polkadot, it's upgradable, right? Now upgradability is cool, and yeah, great, but there are a couple of downsides to it. One of them is you're always running the risk of an insecure upgrade, right? The more upgrades you do, the more chances that a bug creeps in. The second, and the very fact that you can have an upgrade, or rather, the easier you make it to upgrade, the easier you make it to make a governance attack. So this is one downside. The other downside is more of a psychological downside. If a system is easy to upgrade, it means that you don't think too hard about making things simple. Because why would you? You can always upgrade it and simplify it later. You can refactor it and upgrade. You know, there's no great need to actually make it simple and easy to understand and coherent and all the rest of it. No, you just tack bits on because you know that no one else is ever going to have to implement this. You know that you're never going to be judged on the complexity because everyone just sees it as a code blob, not as a protocol. This is not so great, and what it's led to is the Polkadot relay chain becoming pretty bloated in terms of logic. Now, of course, trying to wind back on that, we have been trying to wind back on that for some time now. As you say, moving logic off into system chains. And this is not going to stop. Indeed, it's going to be very much. We're going to see an end goal of this with Corejam, which won't have any logic, barring this VM and what I've just covered on the relay chain. Everything, staking in particular, I'm thinking governance, to the degree that there is like governance for the relay chain, will exist in system chains. There's what I think is sensible to do, what I think is ideal to do, is to get something where it can be formal. What happens in trusted code can be formally specified, yeah, and re-implemented by others. I think if we can get to that point, then, you know, we're doing okay. There is no way whatsoever that Polkadot's current trusted code base, which extends to all of the relay chain, all of that on-chain logic, all the off-chain stuff that the relay chain does, and all of the stuff that the system chains do. Well, if you argue the system chains are trusted, there's no way this could be formally specified. Now, if we say, well, actually, the system chains are application logic, we're still looking at a huge amount of business logic that we would have to formally specify at the moment. And the reason that it's bloated so much is because it's considered a software development endeavor, not a protocol design endeavor. And I fear that this is it's psychological, perhaps, but it's something that is that comes about largely because of the fact it's upgradable. Like designing, if I rewind 10 years doing Ethereum was not upgradable, it's a protocol, right? And so you actually take a lot of time, as you know it's going to be hellish to make any kind of change to it. You take a lot of time to make sure it's as simple as it can possibly be, as general as it can possibly be. Well, we kind of went a different tack with Polkadot. We said, well, look, we're going to be able to upgrade this, so let's just treat it as a general software development challenge. We're not going to care too much about simplicity. We're going to care about, like, getting the functionality in, delivering as fast as possible, etc. We had other priorities, and I think with Corejam, we get kind of the best of both worlds. We get a foundational protocol that is very, very simple, very general purpose, and a trusted element that is minimal, and then everything else goes in system chains, which are inherently upgradable, just because they're not part of the trusted portion. So the fact that we are sort of splitting apart the kernel, which is, I don't know, we'll see, but it could end up becoming hellish to upgrade, right? Hellish to change, and everything else, including things like staking and so forth, which we consider sort of user land, albeit a sort of kind of privileged user land, but still user land. The fact that we're splitting these apart, I think, is quite a good architectural proposition, because it reduces the chance that when upgrading something that is privileged but not kernel level, we don't break the kernel.
Thank you. Regarding the opcons, you mentioned like 20-ish, 23, you mentioned maybe. So anyone who is connected to Polkadot is able to run his own code, even if it's just small. But what are the security implications? Like, have you seen already some cases or tested some cases where you saw that, oh, this is something that everyone who will be using the system and plan execution needs to be careful about?
Could you repeat the first part? Careful about what?
About the VM. So if I understand correctly, the Corejam allows now the execution of custom code, which was not possible before on top of Polkadot,
yes,
right?
on the chain, yeah. Yeah, that's right. So indeed, the VM has to be secure. But I mean, yeah, it is. Probably. I mean, I think that the key thing here is it simple enough to have confidence that it's secure? Like, it can be, it's the more complicated a system is, the less confidence one can have that it acts in the way one expects. And the great thing about PolkaVM is it's incredibly simple. The same question, I could also point out, the same question was asked with the EVM back in 2014. And there was a lot of Bitcoiners saying, but is it really, we turned off bits of Bitcoin script specifically because we weren't sure if it would be secure. And it's like, well, yeah, it's designed to be secure, and probably is. If you put a lot of effort in, you get it audited. VM technology is pretty good these days.
Yeah, I mean, like EVM was, I think, originally pretty secure, right? But what was built and what was executed, it brought us a lot of surprises, right? Like new types of vulnerabilities. So I guess we are expecting some new types of vulnerabilities here, even though it's like way smaller than the EVM, right? But still, like, I would expect there will be some new issues coming out because of new logic and things we just haven't thought about.
I mean, we're getting to the point with its simplicity that it's actually possible to exhaustively check that there are not at least low-level vulnerabilities. So, I mean, if by vulnerabilities you're extending it to include, idiomatic vulnerabilities, for example, like the DAO hack vulnerability, like reentrancy, yeah, sure. Then these are the sort of the unknown unknowns. But again, we can make it a little bit more. We can make it safer by constraining interaction patterns. So, specifically at the moment, in the PVM state environment, so this kind of service interaction environment where services can interact with each other. I mean, just talking about the machine, the machine execution instruction set, it's really trivial. It's super, super trivial. It's very unlikely that there's going to be anything hiding there. But I think when you get to sort of the more emergent things, like when services can interact with each other, that's when you get these kind of slightly strange things happening, like the reentrancy bug that caused the DAO hack. So basically, we've gotten rid of reentrancy. So the PVM doesn't allow reentrancy. Interesting historical point. The original definition of the EVM didn't allow reentrancy either. It was a bug in my implementation, because I misread and I thought it said it was synchronously callable, like when you call between contracts. Actually, in Vitalik's original white paper, it was async, and you did all of the contract calls at the end of the block. They were kind of like post things. But I sort of argued with Vitalik over this when he said, "Oh yeah, that's why it's not working." When there were consensus errors. I argued with him. I said, "Well, look, it's going to be a lot cooler if they can just synchronously operate with each other, because then you can do cunning things like have data gateways and stuff." And he sort of had a think about it, and it was because originally, if you wanted to get data from another contract, you just read its memory. You didn't call into it and ask it for something. You just looked straight there at its storage. And I said, well, isn't it going to be nicer if you can actually make a function call and you can have access to functions? Yeah, okay, we can do that then. So we switched it to synchronous composability. This takes a step back and it says, let's not do that, partly because of reentrancy potential issues. Actually, because the bigger reason is because it doesn't allow for asynchroneity or parallelism while accumulating. If you have asynchronous calls, if all the service interaction calls are asynchronous, then it means that you can execute all of the services, all the accumulation of the services in parallel, actually on chain in parallel. You just say, well, look, they're independent things. They're never going to interact with anything outside of altering their own storage. And any calls that they make into other services, well, that just goes into a sort of queue. And then after all of the services have been accumulated, you then transpose the queue. So instead of being grouped on sender, it's grouped on receiver. Put them into a VEC and then call, hey, you had a transfer made to you. We had a bunch of transfers made to you. Here they are. Here's the code. Here's the memos for that. And then they go and execute that. But again, per service. So you can execute all of the transfers in parallel as well. Or the transfer handling code in parallel. This is kind of, it means that you can only do a one-hop transfer, so you can't transfer as a result of getting a transfer, right? So there's there are some interaction patterns that a smart contract environment would allow that the service environment doesn't. So I don't want to propose Corejam as a smart contract environment. It's really not, but it does have some similarities to smart contract environments. There are some jobs that you might think about doing in a smart contract environment that probably make more sense as a service.
Thank you. My second question. It's a quick one. It's a quick one. So we are building new projects on top of Substrate, but it seems there will be some heavy changes. Like you mentioned, Frame will be changing a lot by end of the year or possibly next year. Mm-hmm. So what is your recommendation? How should we prepare, or we just use the Substrate code base as it is, or we need to keep some things in mind, or some architectural ideas we should be like implementing now, so it will be easier to change when the changes are coming?
So everything should be done pretty much opaquely, so you won't need to parachain teams won't need to do any specific preparations unless sort of told otherwise that that'll be close to the time. But it's unlikely that there's anything that can be done now that would make things like easier later. And really, the aim is to make it a one-off transition. So it's basically like whenever Corejam gets launched, it will be a case of, right, existing parachain stuff stops. Parachains run this script, which and upgrade their cumulus and recompile their PVF, like recompile their code, upload the code to the relay chain, the new code. Probably there'll be a new sort of entry in the relay chain for like next to WASM code for the RISC-V code, and then at some point in the future, like hopefully not very long after, like an hour after or something, then the Corejam thing winds up, starts up, and the parachain just sort of continues just with a new version of Cumulus. So it should be it'll be a big deal, like it'll be a big event, but it won't be a lot of coding, or at least it should be relatively minimal changes. Now, the only thing I can say at the moment that might, if we're thinking, what things might maybe help, try not sending large messages over XCMP. So, honestly, probably shouldn't be doing this anyway. But like, if you got like some large blob, maybe some metadata or piece of code or something, don't send the blob directly over XCMP. Instead, send it over, send it in some off-chain channel like Oracleize it or whatever, and just send the hash over XCMP. This is good behavior anyway, but like it might actually make a difference in the future.
Thank you very much.
Cool.
Hi, Dr. Gavin Wood. I remember a while back, I think it must have been, I don't know, 2015 or 2016, at a conference I asked you about the limits to blockchains, and you were one of the only people that mentioned like theoretical limits or so. And then, around that time, shortly after, Jake Wan from Cosmos started talking about app chains and so forth. And even back then, this notion of like domain-specific blockchains and app chains sort of made sense. But I feel like it's taken almost a decade for like the industry sort of to come to a consensus that perhaps app chains make sense. But most of the industry is approaching this notion, I guess, from what I call it like a caveman or Frankenstein way, where we have this notion of L2s or L3s, and now I've heard L4s, that represent app chains. And so really the question is, as folks here who are, within the Polkadot ecosystem and are building Polkadot-related stuff in parachains, how do we see Polkadot playing a role into this all scalability narratives, and or perhaps, quote unquote, helping the archaic layer ones scale? Or do you feel like we as folks who kind of, building in Polkadot and so forth should kind of just ignore that old world? What is your take on these things?
So I think so there are ways of using Polkadot cores that don't involve parachains. This is already, there are projects already underway that do this, that actually use the Polkadot availability system to provide for decentralized data availability to onto other chains, or projects based on other chains. And it might be that this becomes a more prevalent thing as Corejam becomes a thing, as Agile Core Time becomes a thing, and as we end up with like core time markets. But in general, I find it hard to. I think it's very I think there's two ways of going about this, two ways of like designing and architecting a system. One of them is, get the components right, and people put the components together and make cool stuff. And the other way of doing it is make sure that you have a sort of full spectrum system, make sure that everything is covered so that people can do useful things without having to think too hard about what else they need to bring in to combine to make it. So they're kind of a bit of the same thing, but I would say the key difference is that the componentized form doesn't really think in terms of product. It thinks in terms of just making of the technologies that they go in, and you just make sure all the technologies are there. Whereas the full spectrum thing doesn't necessarily have to be modular. It's really a product that says, right, this product should be a complete solution. And it feels like the question was like, should we intentionally make an incomplete product in order that other incomplete products can utilize this incomplete product and maybe perhaps offer a solution for someone? And I would say no. I don't think intentionally doing that is such a good idea. Now, it's an interesting question in the industry at this point because Ethereum has sort of intentionally gone down that path. Why? Well, I'm sure Ethereum guys will come up with all sorts of good reasons. My personal, cynical perhaps, take on it is that it was too difficult, given a very indecisive polity in control of, if control is the right word, the Ethereum protocol. It was too difficult to come up with a full spectrum solution, a product, an effective product. And so, as a sort of, in an act of desperation, the next best thing was done, which was to design something which is, good design, robust, resilient design, but that doesn't offer a full spectrum solution, and let others figure out the bits that are too difficult to do the core. Now, that's my cynical take on it. And I think these things, often there's a little bit of one thing and a little bit of another thing. I don't think it's the only factor involved here. And I think there are good arguments for why you might want to split things apart. But I think there are also exceptionally good arguments for why you might not. And I think that by offering a full spectrum product, well, you don't need to look to other protocols necessarily to get the job done. But also modularizing it, componentifying it, and making sure that individual parts can be used elsewhere, I think you get kind of the best of both worlds. Does that answer the question?
If it does. I mean, I think you did a great job architecting Ethereum. The opcodes are one of the best things, but I feel like we're almost stuck in this archaic world, and we don't want to move forward from it. And the solutions, if you're an engineer, going down to saying there's going to be an L3 or an L4, and there's like a roll-up on top of a roll-up, makes absolutely no sense. And I think a few people are very frank about this kind of future, right, where others are kind of just going with what everybody says. But that's, I think, part of the reason why we love Polkadot, right? There's more innovations, and like you said, you could build more full-fledged or thought-out solutions. So, thank you.
Cool.
Polkadot LFG.
We're taking the last round of questions. Did you have one lined up? Okay, too sharp.
Hi. So my question is, like, during the presentation, you mentioned about like authorization computation that we were doing in some things that we are doing in core rather than on chain. Mm-hmm. So, like, this seems like a very interesting idea, the way like we can leverage or exploit the hardware that we already have from the validators, other than just doing everything on chain. So can there be like more use cases or something like which I was also trying to explore, is that for example, if there is a system chain or like a chain A which holds a blob of information, and I want to do some computation and post the results on my parachain. Like this thing can happen in a trustless way in core, and then the results go on chain. So I utilize the hardware, and I'm still not like paying as much as fees required or something like that.
So I'm going to try and reformulate the question. Is it possible to pay to do computation, extra computation, on a system chain without going through the system chain and its fee structure itself, and instead going directly onto the core?
Yes.
Yeah. Is this the?
Yeah.
Is it? In principle, yes. Agile core time provides for this circumstance. Now, I would have thought in general you probably don't want to do that because you are you're going to want to not do so much computation that you're going to use an entire block. But I suppose if you had like an entire block's worth of transactions, then you would, and it so happened that purchasing a core for a block was less than the cumulative fees of those transactions. Then yeah, I don't see any reason why you wouldn't be able to just buy a core slice, put the system chain on there, be the block producer, and therefore collect 20% of the. So this is the slight issue. 80% of the transaction fees go to the treasury, and so you would only get 20% of them back. So it would actually have to be a 5x reduction in core time price over the transaction fees price. Now that said, I think there's no great need. The system chain transaction fee structure could probably be reworked fairly easily to make it so that 80% of it didn't go to the treasury if the core time wasn't purchased by the treasury. Because system core time is kind of core time that's purchased by the treasury, right? Economically speaking. And so it could just check in the authorizer. If it's the system authorizer, then burn 80% of the fees and give 20% to the block producer. If it's some other guy authorizer, then just charge no fees. Or yeah, that's probably the easiest thing. Charge no fees.
So that can enable like more use cases and like enable more things and more computation for the projects, and specifically, but what I'm trying to build in that I can leverage more chains and more data.
Yeah, I mean the slight issue perhaps would be that it still has to fit into the system chain. So you have to still author a new block on the system chain. So the system chain kind of collation system needs to know that if you buy a block, if you buy core time and build a block, it should import it. But again, I think this is stuff that probably isn't possible directly at the moment, just because Cumulus doesn't support this use case, but it feels like it's something that could probably be implemented quite easily.
And lastly, addition to it, like, and it won't be like a bad gesture or like under incentivized validator for the validator perspective.
Under incentivized.
Like a validator is running the same hardware, and there is now little extra computation for which he may or may not be rewarded.
So when you say validator, do you mean collator or Polkadot relay chain validator?
Maybe.
Relay chain validator.
Yeah.
Validators are rewarded regardless of whether core time is sold or for how much core time is sold. They're rewarded directly from the issuance. So, no.
Okay. I think that's it.
Cool.
Thank you, Gav, for your time.
Cheers.